In this presentation, we focus on a decision that quietly determines whether a container yard runs smoothly or gets trapped in repeated unproductive moves. The stacking rule. Stacking is not just storage. It is advanced planning for retrieval. The practical question is simple but operationally expensive when answered poorly. When an incoming container arrives, where should we place it so that later retrieval is fast and safe, and the yard crane does not waste time moving containers only to reach other containers? A container terminal is both a transportation system and a storage system. Every placement decision changes the future layout, and that layout later determines how many moves the yard crane must perform to retrieve containers for outbound loading. The most visible symptom of weak stacking rules is the reshuffle. A reshuffle is the kind of move everyone wants to avoid. You relocate a container that is not leaving now, only because it blocks one that must leave sooner. As yard utilization increases, these avoidable moves rise sharply and quickly become a dominant source of delay. Picture a typical yard bay with 6 rows and about 4 to 5 tiers of stacking height. Containers arrive over time, each with a known or predicted departure time, plus attributes like destination and operational priority. The yard team has to apply stacking rules consistently. That means they need a rule that is executable at the moment of arrival, but also strategically protects near-term departures from being buried under late-departing containers. A reshuffle is an unproductive move, moving one container purely to access another container that is blocked underneath it in the same stack. It consumes crane time, increases wear, and introduces additional operational risk. The key point is that reshuffles create cost without creating customer value. When we reduce reshuffles, we directly improve crane productivity, reduce congestion, and improve schedule reliability. 2 stacking strategies commonly appear in practice. Category stacking groups containers by similar attributes such as destination, customer, or service class. This can simplify later sorting, but it can also create blocking when departure times vary inside a category. Residence time stacking uses departure timing as the organizing principle. Containers that must leave sooner should be easier to access, even if that reduces how perfectly we can group by other attributes. This is a combinatorial optimization problem. Each placement changes the future state of the bay, which changes future blocking, which changes future reshuffles. That is why a sequence of locally reasonable choices can still produce a globally poor outcome. There is also an important regime change with utilization. In practice, solutions can differ significantly between low-loaded yard bays, meaning fewer than 15 containers, and high-loaded configurations. So we want tools that give us benchmarks for small cases and scalable rules for real operations. Poor stacking rules show up as extra crane moves, longer truck turn times, missed vessel cutoffs, and higher operational emissions. They also create operational stress, more exceptions, more manual overrides, and more yard congestion. That is why stacking rules are not a minor local heuristic. They define whether the yard is predictable and controllable, or chaotic and reactive. We tackle this problem using multiple tiers. Tier 1 builds a complete mathematical baseline model for stacking decisions and reshuffle logic. Tier 2 provides a classic fast heuristic that can be executed continuously. Tier 1 frames stacking as an integer programming model. The model chooses a storage location for every container and explicitly represents the blocking relationships that create reshuffles. The objective is straightforward in words: minimize the number of reshuffles. The hard part is enforcing the real stacking geometry and connecting it correctly to departure order so reshuffles are derived from the layout, not guessed. We begin with sets that anchor the model to the physical yard bay. We define a set of stack positions, a set of tier levels, and a set of containers. With these, we can represent container I is placed at stack S, tier T, without ambiguity. Once we can index locations, we can index relationships. Blocking and reshuffles are not separate mysteries. They emerge from where containers sit relative to one another and from their departure times. Key parameters include each container's departure time and weight, plus the capacity and geometry of each stack and each tier. We also use a large constant, often called big M, to express certain logical conditions in a linear way. Departure time is the main driver. If an early departing container is placed below a later departing one in the same stack, then at retrieval time the later departing one becomes a blocker, and a reshuffle becomes unavoidable. The first decision variable is the placement decision. It answers a concrete operational question. Is container I placed at stack S and tier T? This is the heart of the model because every downstream relationship depends on placement. If placement is modeled cleanly, blocking and reshuffles can be computed consistently. If placement is vague, reshuffle counts become unreliable, and the model stops being actionable. Next, we introduce variables that capture relationships created by a placement. A blocking indicator becomes active when one container sits above another container in the same stack. A reshuffle indicator becomes active when that blocking relationship conflicts with departure order. This is the bridge between geometry and operations. It converts who is above whom into who will force an extra move later. The objective is to minimize the total number of reshuffles. In plain English, we add up every reshuffle indicator across all relevant container pairs. This objective matches the business goal. When reshuffles go down, crane time is used for productive moves rather than rehandling, and reliability improves. The assignment constraint ensures completeness. Every container must be assigned exactly once to a valid location. Operationally, no container is left unplaced, and no container is stored twice. This prevents two obvious failure modes: the model hiding hard containers by ignoring them, or artificially improving reshuffle counts by duplicating placements. The position capacity constraint enforces that each physical location can hold at most one container. This is a simple rule, but it protects against impossible solutions that look great in a spreadsheet. Without it, the model could stack multiple containers in the same slot and falsely claim low reshuffles. Stacking order enforces physical reality. A container cannot float. If a container is placed at a higher tier, there must be a supporting container below it in the same stack. This constraint ensures that the model's layout could be built in the yard and respects the vertical structure of the bay. Now we formally detect blocking. If container I is placed above container J in the same stack, then I blocks J. The constraint links this blocking indicator to the underlying placement decisions. The purpose is auditability. Blocking is treated as a derived fact that only activates when the placements imply it. A reshuffle is counted when a blocking relationship conflicts with departure order. If a later departing container blocks an earlier departing container, then the crane must move the blocker first at retrieval time. This is the core operational logic in Tier 1. It encodes the true cause of reshuffles and makes the objective meaningful. Placement, blocking, and reshuffle indicators represent discrete facts, so they must be binary. Each one is either true or false. This matters because continuous half-blocking variables would not correspond to an executable yard plan. This visualization helps you see the model in the way operators see the yard. When one container sits above another in a stack, the lower one is not directly accessible. The figure makes the mathematical logic intuitive. Placement creates a stack creates blocking, and blocking paired with departure order creates reshuffles. Consider 5 containers with departure times described as follows. Container 1 departs at time 3. Container 2 departs at time 1. Container 3 departs at time 5. Container 4 departs at time 2. Container 5 departs at time 6. With 3 stacks and a maximum of 2 tiers, one good solution places container 2 at the bottom of stack 1, places container 4 at the bottom of stack 2, places container 1 on top of container 2, places container 3 at the bottom of stack 3, and places container 5 on top of container 3. In this configuration, exactly one reshuffle occurs when container 2, the earliest departure, must be retrieved and container 1 must be moved first. Interpret Tier 1 as a chain of cause and effect. First, we choose placements. Those placements define the stack structure. The stack structure implies blocking. Then blocking combined with departure order implies reshuffles. This is what makes the model operationally defensible. It explains not only the count, but also why reshuffles occur. Exact integer programming becomes expensive as problem size increases. That is why Tier 1 is best used for small cases, planning studies, and benchmarking. In real-time operations, we typically cannot solve a full optimization model for every arrival. That motivates Tier 2, a rule-based method that is fast and consistent. Tier 2 uses a constructive heuristic. Instead of solving a full model, it assigns containers one at a time using a priority-based score to evaluate feasible placement choices. The aim is speed and repeatability. You want a method that can run continuously inside a terminal operating system and still reduce reshuffles in a measurable way. The heuristic evaluates candidate placements using multiple criteria. It estimates reshuffle risk, it penalizes severe stack height imbalance, and it penalizes departure time incompatibilities. Practically, this is the difference between first available slot placement and a policy that anticipates downstream retrieval and tries to protect early departures. Read the flowchart as a simple loop. For each arriving container, evaluate all feasible positions, choose the best scoring position, update the base state, and repeat. This structure makes the method deployable. It is transparent, and you can audit decisions when the yard team asks why a particular placement was chosen. The score function is a weighted combination of penalties. One penalty represents expected reshuffles, another captures stack height imbalance, another captures departure time conflicts. The weights are not arbitrary, they reflect what your terminal values most. If on-time vessel departure is the top priority, you assign a heavier penalty to departure time conflicts. In this code section, the implementation defines the basic data structures for stacks and containers and computes a placement score for each candidate position. The critical operational point is that the score must reflect future retrieval risk, not only immediate feasibility. Otherwise, the heuristic just becomes a slightly smarter first available slot. This continuation selects the best placement, commits the decision, and updates the yard state. Because each placement changes future blocking, the algorithm must recompute scores dynamically after every container is placed. The heuristic is fast and suitable for real-time operations, but it does not guarantee optimality. It trades global optimality for speed and consistency. In a small worked scenario, it yields an expected reshuffle count of 1 and flags high-risk placements, where a late departing container would block an early departing one. Tier 3 introduces a genetic algorithm to explore many alternative stacking rule configurations. Instead of committing to one greedy choice sequence, we evolve a population of candidates. This matters most when the yard is highly loaded and local greedy rules get trapped. The genetic algorithm searches globally and can discover non-obvious trade-offs. The evolution loop is simple to explain. Create an initial population of stacking rule configurations. Evaluate fitness for each candidate. Select the strongest candidates. Create offspring using crossover. Add diversity using mutation. Then repeat. Over generations, the best solutions improve, and the population converges towards stronger stacking policies. A chromosome encodes a stacking rule configuration. Conceptually, it represents preferences or patterns for assigning containers to stacks and tiers, so that a full yard plan can be produced from the encoding. The key requirement is validity. Crossover and mutation must produce meaningful variations that can still be interpreted as executable stacking decisions. Fitness must align with terminal goals. A typical fitness function heavily penalizes reshuffles and also penalizes unstable or highly imbalanced stacking patterns. If fitness is misaligned, the algorithm will optimize the wrong behavior, so defining fitness is the most important design choice in Tier 3. This code section initializes the population and computes fitness for each candidate. Fitness must be computed consistently. If evaluation is noisy or inconsistent, the genetic algorithm will optimize noise rather than true operational performance. This continuation implements selection, crossover, mutation, and the generation-by-generation evolution loop. Elitism preserves the best solutions while the rest of the population explores new configurations. This creates a practical balance between stability and exploration. Genetic algorithms depend strongly on hyperparameters. A strong baseline is a population size of 100, a mutation rate of 0.1, a tournament selection size of 3, and 500 generations. The principle is to keep enough diversity to avoid premature convergence while still allowing the best solutions to spread through the population. In a small demonstration, the genetic algorithm improves configurations over generations, reducing reshuffles compared to random initial rules and often outperforming simple heuristics. The takeaway is that evolutionary search can discover placements that greedy rules miss, especially when multiple objectives conflict under high yard utilization. Tier 4 reframes stacking as a sequential decision problem. A reinforcement learning agent observes the yard state, chooses a placement action, receives a reward, and learns a policy over time. This is valuable when patterns repeat daily but conditions vary. The agent can adapt based on learned experience rather than relying only on fixed hand-designed rules. The state can include current stack heights, the departure times of containers currently in each stack, the weight distribution, and time context that influences urgency. The modeling goal is to include enough information to predict blocking and reshuffle risk without making the state so large that learning becomes unstable. Actions correspond to placement choices. In the simplest form, the action is selecting a stack and a tier for the arriving container, subject to feasibility. In practice, action validity matters. The agent should not waste learning capacity exploring impossible placements, so infeasible actions should be filtered or penalized consistently. Reward design is crucial. We penalize reshuffles and also penalize unsafe or unstable stacking patterns, while rewarding efficient use of space. If reward is poorly designed, the agent may learn unintended behavior like packing space efficiently while creating severe long-term blocking. The reward function combines multiple terms. There is a negative term for reshuffles, negative terms for height imbalance or unsafe patterns, and a positive term for efficiency. This structure forces the agent to treat reshuffles as a primary cost rather than an afterthought. A deep queue network uses a target network update to stabilize learning. In plain language, the learner uses a slowly updated reference network to compute training targets. This reduces oscillation and makes training more stable in complex decision environments. This slide explains the network that approximates action values. Inputs represent the state, and outputs estimate the value of each feasible action. Good state features matter as much as network depth. If the state does not encode blocking risk, the agent cannot reliably learn to avoid it. The learning loop is observe the state, choose an action with exploration, receive reward, store experience, sample batches, and update the network. Over many episodes, the policy improves. The agent learns to avoid placements that create hard-to-fix blocking patterns. This code defines the environment, the state encoding, and the deep queue network model. Practical details like masking infeasible actions and normalizing features can significantly improve training speed and stability. This continuation implements training, replay buffer logic, batch updates, target updates, and evaluation. The goal is to produce a stable policy that generalizes across scenarios, not a brittle policy that works only on one bay configuration. Training results typically show fewer reshuffles than rule-based baselines. A concrete claim is that a deep queue network policy can achieve about 15% fewer reshuffles than traditional baselines. In a test case with 20 containers and 4 stacks, reshuffles drop from 4 down to 2,